Hello, welcome to Electronics Education. This is Vincent Chang. Today we're going to start a new series around the device physics of p-n junction. Device physics of p-n junction. p-n junction in thermal equilibrium. p-n junction in thermal equilibrium, part 1. Let's start with the p-n junction, the concentration on both sides. On the left-hand side is the p-type semiconductor. On the left-hand side is the n-type semiconductor. P-type on the left, the n-type on the right. Let's assume the acceptor atom concentration for p-type semiconductor is 10 to the 18th power per cubic centimeter. On the right-hand side, let's also assume the donor atom concentration for the n-type semiconductor is 10 to the 16th power per centimeter cubic. And based on what we learned before on the fundamental semiconductor physics, on the left-hand side, the whole carrier concentration will be solely determined by the acceptor atom concentration, which is Na. And on the other side, the electron carrier concentration in the p-type is the minority carrier. Because based on the mass action law, it's going to be the Ni square, intrinsic carrier concentration square, divided by acceptor atom concentration Na. On the right-hand side, N, which represents the majority carrier concentration in the n-type semiconductor, electron carrier concentration will be solely determined by the donor atom concentration. And the minority carrier P, the whole carrier concentration, will be Ni squared divided by Nd. So therefore, let's plug in the number. All right, assuming the material is silicon, then the whole on the left-hand side will be 10 to the 18th power. What about electron? Electron carrier concentration will be around 100. On the right-hand side, the majority carrier electron carrier concentration is going to be 10 to the 16th power. The intrinsic carrier concentration square will be 10 to the 20th power. And then 20 minus 16 will be 10 to the fourth power, 10,000. All right. So this is the carrier concentration picture for a p-n junction, for the p-type and also that. So let's now move on to discuss the thermal equilibrium condition for a p-n junction. Let's start with the left-hand side, the p-type semiconductor. So P, the majority carrier concentration is whole, a lot of whole, abundant resources for whole, for positive carrier. And then let's attach an n-type semiconductor. So in the junction is, the p-n junction is formed. And then what? Because if you look at the p-n junction as a whole, and the carrier concentration is not uniform. On the left-hand side, the whole carrier concentration is very high. But on the right-hand side, the electron concentration is very high, but the whole concentration is very low. So the concentration is not uniform. So from a very high on the left-hand side, if we talk about the whole, but on the right-hand side, it's going to be very low. So diffusion is going to happen. So the whole carrier is going to diffuse from the high concentration side to the low concentration side, from the left to the right. In the same way, for the electron, will be from the high concentration on the right-hand side, so going to the low concentration on the left-hand side. And then what? So where's the source for providing whole on the left-hand side? So where's the source? It's the extrinsic, right? The extrinsic. So the source is not actually from silicon, but from what? From the impurity, from the dopant. So on the left-hand side, the dopant is acceptor. So from the acceptor. So if acceptor provide is the source for hole carrier. So when the hole leave the parent, when the hole diffuse, say goodbye to the parent is the acceptor. So then the charge, the ion, will be revealed. What ion? Negative acceptor ion. So if you leave, if you throw away the one hole from the left hand side to the right, and then one negative ion will be revealed based on the charge neutrality. So if we have the two hole leave the P and go into the N side, then the two negative charge will be revealed, will be exposed. And then in the same way on the right hand side, where's the source providing so many electrons? So it's not from the electron, from silicon itself, it's from what? From the parent, from the dopant. So what's the dopant? The donor. Then the electron, when electron leave, then what? When electron going from right to left, then the parents, the charge will be revealed, will be exposed. What charge? The positive donor ion. So when the diffusion happens, the hole going from left to the right, and then electron going from right to the left, then what? Then two types of ion will be exposed. Then what? Then this is the ion separation. This is the charge separation. So then you have the positive charge on the right hand side of the interface and the negative charge on the left hand side of the interface. Then what? We know the electric field line, will be emit from a positive charge and touch on the body of the negative charge, right? And on the body of the negative charge. So electric field line, electric field will be established. So then when you see the electric field, that means what? That means a counter force will be created. That's called drift. Oh, I just want to mention, this electric field, this concept is very important. Have we ever applied a field upon the p-n junction? No. The electric field is not applied. It's from the external. It's from the internal built-in. It's the built-in electric field. It's the inner being. It's the inner force. All right. So it's the inner drive. It's the inner electric field. So electric field is called built-in electric field. So when you see the electric field, then what? You think about what? It reminds you another counter force. It's called drift. So drift, we know the whole charge is going to move along the electric field in the same direction, while the electron is going to move in the opposite direction as opposed to the electric field, right? So this is the drift. So if you look carefully, these two forces, the diffusion on the bottom and the drift on the top, they are opposite to each other, right? So what's the thermal condition? Eventually what? Just this is an open circuit diode. This is the open circuit diode. So when you see a diode, when you see an open circuit diode, when you see open circuit p-n junction, there's no current. So the net current will be zero. The zero net current can be explained by the balance between the two forces. All right, the balance between the diffusion and the drift. So when in the thermal equilibrium condition for open circuit p-n junction, the net current will be zero, should be zero. Zero net current. All right. So we are approaching to the end of the lecture. So two key message I want to convey. Number one, I want to know the microscopic illustration for a thermal equilibrium p-n junction. A p-n junction in a thermal equilibrium condition. Okay, so what's the process? The microscopic process, the diffusion, and then what? The ion separation, right? The negative acceptor ion on the left and positive donor ion on the right. When you think about the ion, follow me, all right? And then what? The electric field is the built-in electric field. The built-in electric field across the junction. Electric field, then what? The drift. The drift what comes up. And in the open circuit condition, thermal equilibrium, there's no current. Because the diffusion force will be balanced, will be canceled out by another force called drift. All right, this is the microscopic illustration for a p-n junction in thermal equilibrium condition. The second takeaway. You see a lot of ion, the negative ion, on the left-hand side, of the interface, right? Here, this is the interface. On the left-hand side, there's a blank area, right? And a lot of I just use the, it's very because it's schematic, right? Okay, so you see two, but what's the concentration for this? For the Na, 10 to the 18th power. A lot of negative ion on the left on this area, all right? So same thing, a lot of donor ion on this area. So you see a lot of negative ion in this area. What does that mean? That means you lose a lot of Hall carrier in this area. That means a lot of Hall carrier are depleted during the process. So same thing, you see a lot of donor ion means what? Means a lot of electron leave the parent body going to the other side. So you see a lot of donor ion means what? Means a lot of numerous the electron was lost, left, going from right to the left. So in this area means the majority carrier are depleted. The majority carrier means the whole carrier on the left-hand side for the p-type, an electron carrier on the right-hand side for the n-type. So this is the region, this is the area where the majority carrier concentration are depleted. So this region is called depletion region. It's called depletion layer. So within the depletion layer, electric field is established. That's the concept I want you to digest. You need to digest this before we move on to the next one. So I hope you received something from this lecture. Thanks for watching.